Okay, so when we last left off, we did a guided example of balancing a chemical equation and completing stoichiometry calculations. What I now want you to do is to write and balance the following chemical equation, and I'd like you to then complete a series of mole-mole conversions. So let's take about 5 minutes and let's work through these problems. So first things first, you need to write a balanced equation for the following expression. Then you need to complete the following 2 mole-mole conversions. And you can submit to me your answers for B and C as a private message, and I'll be sure to respond and provide any corrections and guidance for solving these problems. So let's spend the next 5 minutes working through these problems. So we'll come together as a group at around 2:46, but let's try to write out a chemical equation and use that equation to complete some stoichiometry problems. And in about 3 minutes, we'll focus on writing out the balanced equation just to make sure we're all on the same page. All your responses are correct. Let's take about 1 more minute to at least try to have a balanced chemical equation written. You just change in the message options. You change from everyone to the specific person you want to message. In which case, your instructor, which is my name in the chat. So as it is 2:43, let's focus together on processing this chemical equation in word form and writing out a balanced chemical equation. So for magnesium, it's a monoatomic metal. So as a result, it's just Mg solid. Would someone like to tell me the formula of nitrogen gas? What's the formula of nitrogen gas? N2, exactly right. And then for magnesium nitride, so let's talk a little about this. So magnesium has a 2+ charge. What's the formula of nitride? What is nitride? Nitride, not nitrogen. Nitride is N3-. So it's the nitrogen anion. We then cross our charges, and that gives us Mg3N2 solid. Now that we have our formulas written, we can look at our chemical equation. We see we have 2 nitrogen atoms on the left, 2 nitrogen atoms on the right. We have 3 magnesium atoms on the left, but we only have 1 magnesium atom. 3 magnesium on the right. We only have 1 magnesium atom on the left. So my question to all of you is, what coefficient, what times 1 would give us 3 magnesium atoms? Yep, a coefficient of 3, exactly right. So now that we have our balanced chemical equation, we're now able to actually complete stoichiometry calculations. So in this first case, we're asked to calculate the moles of magnesium nitride formed by complete reaction of 10 moles of magnesium. So we're trying to calculate the moles of magnesium nitride, and we're starting from the moles of magnesium. So what I want everyone to do is, we have our balanced chemical equation. I'd like you to take about 2 minutes and try to complete the following mole-to-mole conversions. So we'll come together to discuss in about 2 minutes, and you can send me your potential responses for parts B and C using the chat feature. Victoria, your response is perfectly correct. So we'll spend about 1 more minute on tidying up. Francisco, your response for part B also is perfectly correct. So we'll spend about 1 more minute tidying up our responses, and then we'll discuss each of these problems. Okay, so as it is 2:48, we'll now resume and discuss these problems after we had some time to work through each of these problems individually. So first and foremost, we're starting with 10.0 moles magnesium, and we're trying to calculate the moles of magnesium nitride. So starting off with 10.0 moles of magnesium, looking at our unit conversion map, what units do we need on top in our conversion factor? What units are we trying to calculate? What units are we going to have on top? Moles of what is going to be on top? Yep, exactly. The moles of magnesium nitride. Okay, and what units are going to be on the bottom? What units are going to be on the bottom? Yep. Okay, so for the moles of magnesium nitride, how many moles of magnesium nitride are we producing in this reaction? How many moles of magnesium nitride are we producing? What's our coefficient for magnesium nitride? What's our, yep, 1. And what's our coefficient for magnesium? How many moles of magnesium are reacting? 3, exactly right. So that in turn gives us 10 over 3, which is 3.33 moles of magnesium nitride. Perfect. Let's keep going now. We're next asked to calculate the moles of nitrogen consumed when 10 moles of magnesium reacts. So then, we are trying to calculate the moles of nitrogen, and we're given the moles of magnesium. So continuing on from this, we're starting with 10.0 moles of magnesium. If we think about our conversion factor logic for a moment, we're trying to go, sorry about that. We're trying to go from the moles of magnesium to the moles of nitrogen. So we're going to have moles of nitrogen on top and moles of magnesium on the bottom. And my question to all of you is, first and foremost, how many moles of nitrogen are consumed based on our chemical equation? Following our stoichiometry, we'd have 1 mole of nitrogen consumed. And how many moles of magnesium are reacting with that 1 mole of nitrogen? How many moles of magnesium are reacting? 3, exactly right. So that in turn gives us 3.33 moles of magnesium. Oh, whoops, sorry, moles of nitrogen. Our units cancel, we're left with moles of nitrogen on top. Any questions on this example? The only thing that's new is that we had to write our chemical equation, we had to balance our chemical equation. Beyond that, this is all standard stoichiometry. Any additional questions on this example? If not, we'll continue on with a few more examples. So, this time we're asked to write and balance the chemical equation and do a series of mass-to-mass conversions. So these questions are very similar to what you'd see on an exam. So we're given that carbon monoxide gas reacts with hydrogen to produce liquid methanol. So to help me out on this, what's the formula of carbon monoxide gas? What's the formula of carbon monoxide? If we're writing an equation, yep, CO, yep, that's exactly right. Carbon monoxide is CO gas. What is the formula of hydrogen gas? H2, yep, exactly right. And methanol is CH3OH. Okay, so is this equation balanced as written? Is this equation balanced? I see a lot of people saying no. Okay, so then, exactly right. We have 2 hydrogens on the left, we have 4 hydrogens on the right. 2 times a coefficient of 2 would give us 4 hydrogens. So we put a coefficient of 2 in front of H2. Perfect. Now that we have our balanced equation, we are able to start our mass-to-mass conversions. So we're asked to calculate the mass of methanol produced from complete reaction of 28 grams of carbon monoxide with hydrogen. Okay, so we're trying to calculate the grams of methanol, and we are given the grams of carbon monoxide. So just as a question, in order for us to convert between these 2 masses, what units are we going to go through to complete this mass-to-mass conversion? Given that we have the chemical equation, what units are we going to go through? Yep, the mole-to-mole conversions. We're going to go from grams of carbon monoxide to moles of carbon monoxide. And then from moles of carbon monoxide, we'll calculate the moles of methanol. Perfect. Now that we have our solution map in place, we're going to put our input units. So our starting units are 28 grams of carbon monoxide. Following our solution map, we're going to go from grams of carbon monoxide to moles of carbon monoxide. And we know in 1 mole of carbon monoxide, we have how many grams? What is the molar mass of carbon monoxide? Would someone like to help me out in that? What's the molar mass of carbon monoxide? Yep, 28 gram per mole. Exactly right. Now let's get to the really interesting part here. We're going from moles of carbon monoxide to moles of methanol. So we'll have moles of methanol on top, and we'll have moles of carbon monoxide on the bottom. How many moles of methanol are produced in this reaction looking at the chemical equation? How many moles of methanol are we making in our chemical equation? 1. And how many moles of carbon monoxide are we reacting in our chemical equation? Also 1. Exactly right. Finally, we need to go from moles of methanol to grams of methanol. And to do that, we're going to have grams of methanol on top and moles of methanol on the bottom. This is, in effect, the molar mass of methanol. So then, let's really quickly, I'd like you to take a moment and I'd like you to calculate the molar mass of methanol, just to make sure you're still comfortable doing that. So what should we fill in for the molar mass of methanol? Yep, 32. So let's show that. So we have 12 grams for carbon plus 1 gram times 4 for hydrogen. And then for oxygen, we have 16. We add this together, we get 32 grams of methanol per mole of methanol. We're now ready to punch this into our calculator, and at the end of our calculations, we get 32 grams of methanol. Perfect. So let's look at the next problem. Let's look at the next portion of this problem. We're asked to calculate in the next part the mass of hydrogen gas required for a complete reaction of 28 grams of carbon monoxide. So we're trying to calculate the grams of hydrogen starting from the grams of carbon monoxide. Now, just like before, we're going to convert to moles to utilize our chemical equation. So we're going to go from grams of carbon monoxide to moles of carbon monoxide to moles of hydrogen to grams of hydrogen. Okay. So now that we have our solution map prepared, we're going to start with our 28 grams of carbon monoxide. And just like before, to go from grams to moles, we're going to divide by our molar mass. So we have 1 mole of carbon monoxide per 28 grams. Now for the interesting part. How many moles of hydrogen do we need to react with how many moles of carbon monoxide? So let's take a look at our equation. How many moles of hydrogen are reacting in our chemical equation? How many moles of hydrogen are reacting in our chemical equation? I see a lot of people typing 2. That's exactly right. Now, looking at our chemical equation once again, how many moles of carbon monoxide are reacting? 1, exactly right. So we have 2 moles of hydrogen reacting for every 1 mole of carbon monoxide. Finally, we need to do a mole-to-mole conversion, and how many grams of hydrogen are present in 1 mole of hydrogen? What is the molar mass of hydrogen? Note, I'm saying hydrogen is in the molecular form. Would someone like to volunteer? What's the molar mass of hydrogen? 2, exactly right. 1 times 2 is 2. Perfect. So we punch this into our calculator and we get 4.0 grams of hydrogen. Just to respect the fact that our input has 2 sig figs, our output has 2 sig figs, because all of these intermediate numbers are exact, or functionally exact. Does that make sense so far? Everyone comfortable with these examples? Can I get some feedback in the chat just to make sure everyone's comfortable with this and I'm not going too fast. Okay, perfect. So I'd like you now to tackle the following set of questions. So I'd like you to write and balance the following chemical equation. And then in turn, I'd like you to perform the following mass-to-mass conversions. And you can message me your responses as a private message, and I'll be more than happy to respond and provide feedback. So let's spend about 5 minutes working through this problem, and we'll discuss the balanced equation in about 3 minutes. So focus on getting a balanced written equation first, because that's the only way you can really do stoichiometry problems. Francisco, your set of coefficients are exactly correct. Victoria, you're exactly correct for the formula. Yep, exactly right. We'll spend about 2 more minutes before we write down the balanced equation. Oh, Mariano, I would double check your calculations. Francisco, your response looks perfect. Haral, your response for the first mass conversion is correct. So as it's been 3 minutes, let's focus on writing out a balanced equation from this word statement. So aluminum, so Al, solid, reacts with oxygen gas. We already know the formula of oxygen gas is O2 to give aluminum oxide. Would someone like to propose a formula for aluminum oxide? Would someone like to propose a formula for aluminum oxide? Yep, exactly right. So we have aluminum, which is Al3+, oxide, which is O2-. We cross our charges, and that gives us Al2O3 solid. Perfect. Now, is this equation currently balanced? No. So then, just to showcase the logic, we have 2 aluminum atoms on the right, so we need 2 aluminum atoms on the left. We have 2 oxygen atoms on the left. We have 3 oxygen atoms on the right. So we're going to cheat, and what we're going to do is we're going to use a fractional coefficient. So we're going to guess some fraction to give us 3 oxygen atoms, in which case we'll pick 3/2. Yep, so we'll guess a fraction of 3 over 2, and then to get rid of our fraction, we're going to multiply all of our coefficients by 2. That in turn gives us the following balanced equation. So we have 4 aluminum solid plus 3 O2 gas leads to 2 Al2O3 solid. Perfect. So here's our complete balanced chemical equation. Now I'd like us to take another 2 to 3 minutes and complete these mass to mass conversions. And when I'm asking to calculate the mass of aluminum oxide produced, it's related to the question 2. And don't be shy to message me privately with your calculated mass of oxygen and the calculated mass of aluminum oxide. And Francisco, your response is perfectly correct. We'll spend about 2 more minutes working through these mass-mass conversions, and don't be shy to message me. Yes, part C is coming from the answer you got for part B. Exactly right. Yes, the next homework will focus on stoichiometry. And we'll discuss in about 1 minute. Please don't be shy to send me any of your responses, and I'd be happy to provide feedback. Victoria, your response is perfectly correct for that portion. Alicia, your response is also correct. Okay, so let's discuss this in detail. So we are asked to calculate the mass of oxygen. So we want to calculate the grams of O2, and we are given the grams of aluminum that we want to react. So just like before, in order to complete this mass to mass conversion, we are going to go through units of mole. So we're going to go from moles of aluminum to moles of oxygen to grams of oxygen. Okay, so now that we have our solution map in place, we're going to plug in our starting value. So we're starting off with 54 grams of aluminum. And my question to all of you, if we're going from grams to moles, what conversion factor are we going to use? What conversion factor are we going to use to go from grams to moles? And don't be shy to type in chat. Yep, the molar mass. So in 1 mole of aluminum from the periodic table, we know that consists of 27 grams of aluminum. Now here's for the part that's new. To go from moles of aluminum to moles of oxygen, how many moles of oxygen do we have reacting in our balanced chemical equation? How many moles of oxygen do we have reacting in our balanced chemical equation? What's the coefficient for oxygen? And don't be shy to type in chat. 3, yep, exactly. We have 3 moles of oxygen. And how many moles of aluminum are reacting in our balanced chemical equation? 4, exactly right. Finally, if we want to go from moles of oxygen to grams of oxygen, how many grams of oxygen are in one mole of oxygen? How many grams of oxygen are in 1 mole? What's the molar mass of oxygen? O2? 32. Exactly right. So all we have to do now is punch it into our calculator. And at the end of our calculation, we get 48 grams of O2. Okay, let's tackle this next part. We're asked to calculate the mass of aluminum oxide produced. So we're going, in this case, from grams of aluminum, this time to grams of aluminum oxide. So just like before, we're going to go through moles of aluminum and then convert to moles of aluminum oxide. Okay. Now that we have our solution map prepared, just like before, we're going to go from our 54 grams of aluminum and we're going to convert to moles of aluminum using our molar mass. So this part is exactly the same as before. Now for something a little bit new. If we're going from moles of aluminum to moles of aluminum oxide, my question to you is, how many moles of aluminum oxide are reacting in this case? How many moles of aluminum oxide are reacting? I see responses of 2. Yep, that's exactly right. And how many moles of aluminum react to generate our aluminum oxide? How many moles of aluminum are reacting in this case? Yep, 4. Exactly right. Finally, if we want to calculate the grams of aluminum oxide, how many grams of aluminum oxide do we have per mole? Well, from here, my question to all of you is, what is the molar mass of aluminum oxide? Let's take a moment just to calculate that. Let's take a moment to calculate the molar mass of aluminum oxide. And don't be shy to type it in the chat. Here, all your response is perfectly correct. So for aluminum, we have 27 times 2 plus 16 times 3 for oxygen, and that in turn gives us about 102 gram per mole. Once we punch this entire expression in our calculator, we get a total of 102 grams of aluminum oxide that we then round to 1.0 times 10 to the second grams of aluminum oxide, just to respect the fact that our input has 2 sig figs. Does that make sense so far? Everyone comfortable with these stoichiometry examples? Any questions so far? Okay, I don't see any additional questions, so let's keep going. So let's look at another mass conversion. So let's make sure we're really practiced writing out balanced equation and completing mass conversions. So I'd like you to take a few moments and tackle the following problem. And you can send your responses for parts 2 and 3 to me, and I'll provide you feedback. So let's take about 3 minutes to make our balanced chemical equation, and another 3 minutes to complete these mass-mass conversions. And don't be shy to send me your responses as a private message. Francisco, your response is perfectly correct for the coefficients, and Hiral, your response is perfectly correct for the coefficients. Oh. Just please make sure to mute unless you have a question for the discussion. And don't be shy to send a message with your proposed balanced coefficients. Let's check. So as it is 3:17, we're gonna work through now the balanced chemical equation. So aluminum is just Al solid. It's just an atomic element. Iron 2 oxide. Would someone like to propose a formula? Oh, sorry. Would someone like to propose a formula for iron 3 oxide? Would someone like to propose a formula for iron 3 oxide? Yep, Fe2O3. So we have iron 3 plus, O2 minus. We cross our charges, and that gives us Fe2O3. Solid. Perfect. Okay, continuing on. Iron is just Fe solid, and aluminum oxide, we have Al3 plus and O2 minus. We cross our charges, and this gives us Al2O3 solid. Okay, now my question to all of you is this equation balanced as written? Is this equation balanced? No, of course not. We have different numbers of aluminum and iron. Exactly right. So then, if we have 2 aluminums on the right, what coefficient do we need for aluminum on the left? What coefficient do we put in front of aluminum? 2, exactly right. If we have 2 irons on the left, what coefficient do we put in front for iron? 2, exactly right. Perfect. So now our equation's completely balanced. So let's rewrite our balanced equation down below for our reference. So we have 2 aluminum solid plus iron 3 oxide leads to 2 iron solid plus aluminum oxide. This is the classic reaction of thermite, in case you were curious. It's very exothermic. So we'll check through Hiral's response for question 2. So let's take a few minutes. Let's take about 3 minutes to work through parts 2 and 3, and then we'll come together in a few minutes to share our responses. And don't be shy to send a message, and we'll be resuming our discussion and going over the solutions for the remainder of this problem in about 1 minute. But don't be shy to send me your responses as a private message, just so that way I can provide some feedback. Okay, so let's discuss our solution and let's discuss our thought process for each of these problems. So we're asked to calculate the grams of aluminum oxide produced when 41.5 grams of aluminum react. So we're trying to calculate, we want to calculate the grams of aluminum oxide, and we are given the grams of aluminum. So as this is a typical stoichiometry problem, we're going to go through units of moles in order to use our chemical equation and perform a mole-to-mole conversion. Now that we have our solution map established, we're going to begin our unit conversion process. So we write out our starting unit. So we have 41.5 grams of aluminum. Okay, and we're going from grams of aluminum to moles of aluminum. So in 1 mole of aluminum, we have how many grams? In 1 mole of aluminum, we have how many grams? 27, exactly right. Now for the new part. How many moles of aluminum oxide are generated in this reaction? How many moles of aluminum oxide are generated? 1, yep. And how many moles of aluminum are reacting to generate that aluminum oxide? What's our coefficient for aluminum? What's our coefficient for aluminum? 2, exactly right. Finally, to calculate the mass of aluminum oxide, we need to calculate the grams of aluminum oxide in 1 mole of aluminum oxide. Just 1 moment. Let me 1 moment to reopen OneNote. Give me 1 second. I'm just going to reopen OneNote. Sometimes it Okay, so let's fill in. So we're trying to calculate the grams of aluminum oxide in 1 mole of aluminum oxide. And we've actually calculated this molar mass previously as 102 grams per mole. Now all we have to do is punch this into our calculator. So let's do that really quickly. So we have 41.5 over 27. Times 1/2 times 102. And that in turn gives us 78.38 grams of aluminum that we round to 3 sig figs, giving us 78.4, aluminum oxide, which in turn gives us 78.4 grams of aluminum oxide. So Hiral, your response for the first question was perfectly on point. So let's tackle the next part of this question. And I really want us to be practiced with this, as stoichiometry is really fundamental towards the general chemistry sequence. We're next asked to calculate the grams of iron produced when 41.5 grams of aluminum react. Okay, not too bad. So we're trying to calculate the grams of iron. And we are given the grams of aluminum. So we're going to calculate the moles of aluminum, and then using our chemical equation, we can calculate the moles of iron. So this first chunk where we're calculating the moles of aluminum is going to be exactly the same in this expression. So we're going from grams of aluminum to moles of aluminum. Okay, now for the new part. When we're going from moles of aluminum to moles of iron, how many moles of iron are produced per how many moles of aluminum? What is our mole to mole ratio? So let's start to get a little bit faster at putting together our mole to mole ratio. So what's our mole to mole ratio in this case of iron to aluminum? 2 to 2, exactly right, exactly right. And then finally, to go from moles of iron to grams of iron, we know that we have 55.6 grams of iron in 1 mole of iron. And all we have to do now is punch that into our calculator. It's not too bad. I really enjoy these one-line setups because they help avoid errors. If you're just entering numbers one at a time in your calculator, it's easy to get lost if you don't have your conversions organized in a cogent, easy to read manner. It also makes it easier for me to grade your work and provide partial credit in the event you made a calculator error. So after punching this into our calculator, we get 88.459 grams of iron, which we round to 3 sig figs to give us 88.5 grams of iron. Perfect. Any questions so far? Any questions so far on these stoichiometry examples? Is everyone comfortable solving these examples? Okay, so we're going to skip the example on page 54, and we're going to broach now a really critical idea in chemistry, which is concerned with the idea of limiting reactants. So we're on page 55 now of the notes. So just practically, some reactants work best with excess reactant. Examples of this are combustion reactions. In general, if you have a material that's very valuable, you want to use an excess of your cheaper reagent rather than an excess of your expensive reagent. So product formation is limited by the moles of each reactant and their stoichiometry. So the limiting reactant is a very specific definition where it's the reactant that is completely consumed first during a reaction, preventing the reaction from proceeding further. The way I like to think of it is if you have a car and you run out of gas, your car is going to stop moving. It doesn't matter if you have your car, if your car has perfectly oiled and it has all the windshield wiper fluid that you'd need. If you're out of gas, your car is not going to move any further. To help us see how limiting reactants function using some real world examples, let's suppose you're watching a lollipop factory and to make a lollipop we need a stick and a piece of candy. So let's try to answer this question. How many lollipops can we make with 6 sticks and 4 pieces of candy? Okay, so I'm going to draw the sticks. Okay, so I have 6 sticks. I have 4 pieces of candy. So would someone like to type in the chat, how many lollipops can I make? What's the maximum number of complete lollipops I can make? 4, exactly right. I have 4 pieces of candy, so I can make 4 lollipops. and left over, I have 2 sticks. So one way that we can think about this is that our candy is limiting. And we know if we start with 4 pieces, we know that we make 1 lollipop per candy, and that in turn gives us 4 lollipops. Does that make sense? So it's very easy to see in this case because our stoichiometry is 1-to-1. Let's try to apply this to a more chemical example, and I'm going to color code it. How many moles of zinc sulfide are produced by a reaction of 6 moles of sulfur and 4 moles of zinc? So we have the zinc reacting with sulfur solid to generate zinc sulfide solid. So just like our lollipop example, do we have a 1-to-1 stoichiometry? Is our mole to mole ratio 1-to-1 in this case? Yes. So then if we start off with 6 moles of sulfur, and we have 4 moles of zinc, 1, 2, 3, 4. My question to all of you is, how many moles of zinc sulfide can we make if our stoichiometry is 1-to-1? How many moles of zinc sulfide can we make? So to make zinc sulfide, we need 1 mole of zinc and 1 mole of sulfur. So as we can see, we can make a total of 4 moles of zinc sulfide, and left over, just like our lollipop and stick example, we also have 2 moles of sulfur excess. Does this logic make sense to everyone? Is everyone visualizing what's going on for the limiting reactant? You consume both your reactants based on your stoichiometry, and your limiting reactant is a species that is consumed first in the chemical reaction and limits reaction progress. We run out of zinc in our reaction before we run out of sulfur. Okay, now let's talk about another example, and this is really important to understand. The limiting reactant is not necessarily the reactant with the least number of moles. It's not the smallest number of moles. It's based on the stoichiometry. And to give you a classic example, a sandwich requires 2 pieces of bread and 1 piece of cheese, okay? So here's our stoichiometry. So we have 2 bread plus 1 cheese gives us 1 sandwich. So here's our chemical equation. So then, by the same token, if we have 4 pieces of bread, and 3 pieces of cheese, how many sandwiches can we make? Just by matching. How many sandwiches can we make? If we need 2 pieces of bread and 1 piece of cheese per sandwich. So I see a lot of people saying 3. You're focusing a lot on the number of cheese, but do we have enough bread to make sandwiches from all of these pieces of cheese? Ah, I see people starting to correct. Exactly. We can only make 2 sandwiches because for our 4 pieces of bread, we use up 2 pieces of cheese. So in effect, we are able to make only 2 sandwiches, plus we have a piece of cheese left over. So even though we have more moles of bread, even though we have more moles of bread, if we look at our stoichiometry results in bread being consumed faster than our cheese. So you always need to consider our stoichiometry when you assess limiting reactants. Does that make sense to everyone? Does everyone understand how we're not just counting moles, we're considering the stoichiometry? We use up 2 pieces of bread to make a sandwich. So we run out of bread before we run out of cheese. Does that make sense to everyone? Any questions on this analogy? Everyone's quiet in the chat. Any questions I can address? Okay, so let's get out of these somewhat these real world examples, and let's focus a little bit on some chemistry here. So tin reacts, so tin, which I'm going to think of as our cheese, is going to react with chlorine. It reacts with 2 molecules of chlorine to yield tin tetrachloride. So if we have 4 moles of chlorine and 3 moles of tin, following our sandwich analogy, if our tin is our cheese and our chlorine is our bread, how many moles of tin tetrachloride or tin 4-chloride can we make? How many moles of tin 4-chloride do we make? 2. Exactly right. And the reason for that is we start with 4 moles of chlorine, and we know we get 1 mole of tin tetrachloride for every 2 moles of chlorine, and that in turn gives us 2 moles of tin tetrachloride. Stoichiometry at work. And the reason why chlorine is our limiting reactant is we use up all of our chlorine first in our chemical reaction. Does this analogy make sense? Does everyone visualize limiting reactants a little more clearly now? The limiting reactant is the reactant that's consumed first in our chemical reaction. Okay, if we don't have any other questions, let's talk about some methods to tackle limiting reactants. The first of which is titled the product method. So let's talk a little bit about the product method. So in the product method, first things first, what you're going to do is you're going to calculate the moles of each reactant, okay? You're just going to get to moles. That's always your goal in stoichiometry, mass mole conversions. In general, chemistry functions best when you're going through moles. Next, you're going to calculate the expected moles of product produced by complete reaction of each reactant using the chemical equation stoichiometry. Okay? The reactant that produces the least product is limiting. Now, if needed, you can calculate the amount of each reactant consumed using the moles of product produced and the chemical equation stoichiometry. So this is your guide. I'm not expecting you to memorize this, but through practice, you're going to be using all of these steps, okay? I always like to organize things in steps to help me if I'm ever getting stuck solving a problem. I have some steps to refer to. Okay. Let's talk a little bit about this. So here is our classic conversion map, just for your reference. And let's try to deal with the following problem. So we have calcium hydroxide is reacted with sulfuric acid to yield calcium sulfate and water. Okay, we have a word equation to work with. That's always fun. We're asked to calculate the moles of calcium sulfate formed when 3 moles of calcium hydroxide and 4 moles of sulfuric acid are mixed. Maybe it's just me, but this reminds me a lot again of our bread and cheese example. So first things first, let's write a chemical equation. First, what would someone like to propose a formula for calcium hydroxide? Would someone like to propose a formula for calcium hydroxide? What's a formula for calcium hydroxide? Yep, exactly right. So we have calcium 2 plus, OH minus, we cross our charges. That in turn gives us CaOH2. Perfect. Would someone like to provide me the formula for sulfuric acid? Would someone like to provide me the formula for sulfuric acid? H2SO4, exactly right. So we have H plus and SO4 2 minus. Remember, sulfuric acid is derived from sulfate. So we get H2SO4, perfect. And in turn, we're gonna make calcium sulfate. Would someone like to provide me the formula for calcium sulfate? Yep, CaSO4. Just like before, Ca2 plus, SO4 2 minus, we cross the charges. And remember, you simplify your coefficients. So 2 to 2 simplifies to 1 to 1. And we're also making some water, H2O. Now, looking at this equation, is this equation balanced as written? Is this equation balanced as written? Is this equation balanced? This is very critical. If we don't have a balanced equation, we're stuck. No, it's not, right? So counting on the left-hand side, we have a total of 4 hydrogens and 6 oxygens. On the right-hand side, we have 5 oxygens and 2 hydrogens. So what coefficient do we need to put in front of water? What coefficient do we need to put in front of water to balance hydrogen? 2 times what is equal to 4 hydrogens? What coefficient are we plugging in? 2, exactly right. Perfect, and that gives us also 6 oxygens. So now we've balanced our equation. This should be a very fast step. You want to get really fast at balancing equations. The less time you spend balancing, the more time you spend actually solving the stoichiometry problem. Okay, now what we're going to do is we know that we're starting off with 3 moles of calcium hydroxide, and we also know that we're starting off with 4 moles of sulfuric acid. Now what you're going to do is you're going to convert each of these moles of reactants to moles of calcium sulfate product. Okay, that's what you're going to do. And then once you have the moles, you're going to compare the moles. So we have 3 moles of calcium hydroxide. And my question to all of you is, based on our stoichiometry, how many moles of calcium sulfate are produced per how many mole of calcium hydroxide? What's our mole to mole ratio from products to reactants? What's our mole to mole ratio? Would someone like to volunteer? What's our mole to mole ratio for calcium sulfate? Yep, I see a lot of 1 to 1. Good, good. Okay, so we'd expect for our calcium sulfate, for our calcium hydroxide, we'd make 3 moles of calcium sulfate. Okay, let's do the same thing for sulfuric acid. So we have 4 moles of sulfuric acid. And we also know that we have 1 mole of calcium sulfate per every 1 mole of sulfuric acid that reacts. And that in turn gives us 4 moles of calcium sulfate. Now we compare our two expected amounts of products. And I'd like you to type in chat which reactant produces the least amount of product. Which reactant is limiting? Which reactant is limiting? Which reactant makes the least amount of product? And don't be shy to type in chat. Just compare the amount of product produced. Which one makes the least amount of product? Calcium hydroxide or sulfuric acid? Yep, I see a lot of people responding. Calcium hydroxide, that's exactly right. Calcium hydroxide is limiting because when completely consumed, it makes the least amount of product. For sulfuric acid, one thing I want you to note, sulfuric acid does not actually make 4 moles of calcium sulfate. You run out of calcium hydroxide before you're done reacting all of your sulfuric acid. So then, if you want to calculate the excess reactants, what you do is you take your 4 moles of sulfuric acid and then you subtract your 3 moles of calcium sulfate, and you use your stoichiometry to go from moles of product to moles of excess reactant, okay? So we know that we have 1 mole of sulfuric acid per 1 mole of calcium sulfate produced. And in turn, after we resolve this expression, we have 4 minus 3, which gives us 1 mole of H2SO4 left over. Does this process make sense? Do we understand the idea and logic behind it? So to calculate the amount of excess reactant remaining, you take the moles of product, you convert it back to moles of excess reactant using our stoichiometry. Is everyone comfortable with this example? Any questions on limiting reactants? Everyone's pretty quiet in chat. I know everyone's getting a little exhausted. We're almost done. We'll cut the lecture short in a few minutes. So we completed this problem. What I want you now to do, just to check that you understand the logic behind this, is to take the following equation and convert it from a word equation into a balanced chemical equation. Then I'd like you to tell me the moles of magnesium chloride produced from this reaction, accounting for limiting reactants, and then I'd like you to tell me the moles of remaining reactants. So let's take about 5 minutes to work through this example, and then we'll come together to discuss in about 3 minutes to write the chemical equation, and then in another 3 minutes, we'll go over the full solution. As part of the calorimetry lab, there is a limiting reactant at play, but as we didn't quite get to it before we ran the simulations, I told you that the limiting reactant for the calorimetry lab is going to be your sodium hydroxide. But you now have the tools to actually prove that to yourself. You can calculate the moles and show that sodium hydroxide is limiting for the calorimetry lab. That's a very good question to ask. Thank you for asking it. And don't be shy to send your responses for part 1 and 2 of this question to me as a private message, and I'll be more than happy to provide you some feedback. Yep, here all your response looks correct for your coefficients. Now all you have to do is calculate the moles of product and identify the limiting reactants. And we'll discuss the balanced equation in about a minute and a half more. Okay, so let's talk through and let's generate a balanced equation for this reaction. So magnesium is just Mg solid. Aluminum chloride is AlCl3 solid. Would someone like to propose a formula for magnesium chloride? Would someone like to provide a formula for magnesium chloride? Someone like to, yep, MgCl2, okay. Okay, and aluminum metal, which is Al solid. So, one trick to quickly balance equations, especially when you have ions involved, is you can use the least common denominator rule. So we have 3 chlorines on the left, we have 2 chlorines on the right, so we just take the least common denominator. So least common multiple rule, sorry. 3 times 2 gives us 6, 2 times 3 gives us 6. So we put a 3 in front of magnesium chloride, a 2 in front of aluminum, another 2 in front of aluminum on the right, and a 3 in front of magnesium. Does everyone remember this least common multiple trick? Does this look familiar to everyone? This is one of the tricks that we discussed to balance chemical equations. It's quite handy. It allows you to avoid having to break out half notation or anything like that. It's especially useful for when you have one ion found in compounds on both sides of the chemical equation. Okay, so now that we have our balanced chemical equation, let's take about 2 more minutes and let's calculate the moles of magnesium chloride formed. And remember, just like our bread and cheese example, the limiting reactant is not always the species with the least number of moles. So always remember to go through and use your stoichiometry and compare the moles of product produced. So let's take a few minutes to do that, and we'll discuss at 3:57. and we'll discuss this problem in about another minute. Don't be shy to send me your responses as a private message, just so that way I can help check your work. It's always important that you're practicing going through these problems, especially when your instructor is here to help check during these guided problem sessions in lecture. I would double check your calculation, Hirol. Okay, so as it is 3:57, let's discuss this problem. So first things first, we know that we have 2.5 moles of magnesium. So let's convert our moles of magnesium to moles of magnesium chloride. So let's answer the question, how many moles of magnesium, how many moles of magnesium chloride do we have per mole of magnesium that reacts? What's our mole to mole ratio? What's our mole to mole ratio of magnesium chloride to magnesium? What is our mole to mole ratio? 3 to 3, exactly right. And after calculation, we get 2.5 moles of magnesium chloride. Wonderful, wonderful. Let's continue on. We have 2 moles of aluminum chloride, and we have, how many moles of magnesium chloride do we have per mole of aluminum chloride? What is our mole to mole ratio? Yep, Hirol, you're exactly right for the first part. So just to make sure we're discussing, yep, thank you, Alicia. We have 3 moles of magnesium chloride per 2 moles of aluminum chloride. And thank you, Mariana, as well. Your response is perfectly on point. And that in turn gives us a predicted theoretical yield of 3 moles of magnesium chloride. Now, comparing the amount of product produced from each of our reactants, which reactant is limiting? Magnesium or aluminum chloride? Which reactant is limiting? Magnesium or aluminum chloride? Magnesium, exactly right. One thing I want you to keep in mind, magnesium chloride is the product, but what I'm asking is which reactant is limiting. So in this case, this amount of magnesium chloride is produced from magnesium, ergo we conclude magnesium is limiting because it generates less product when it completely reacts. Does that make sense? Okay, perfect. So now for our next point, we need to calculate the amount of excess reactant remaining. So we're going to take our 3 moles of we're going to take our moles of excess reactant. So we have 2 moles of aluminum chloride. We are going to subtract our moles of product, which is 2.5 moles of magnesium chloride. And we're going to convert this into our moles of excess reactant by taking and using our stoichiometry. So looking at our moles of aluminum chloride per mole of magnesium chloride generated, we consume 2 moles of aluminum chloride per every 3 moles of magnesium chloride generated. So if we punch that into our calculator really quickly, let me break out my calculator. We have 2 minus 2.5 times 2 over 3. And that in turn gives us 0.33 moles of aluminum chloride, which we round to 0.3 moles of aluminum chloride excess. Is everyone comfortable calculating the mass of excess reactant remaining in a chemical reaction? Does this make sense so far? So this is a good stopping point. So we weren't able to finish the entirety of this chapter, but we'll certainly finish it next class session. I want you to take a look at some of the homework. I'll have some titled stoichiometry and balancing chemical equations. I want you to practice some of those examples. All of the homework assignments will be posted this weekend and due next Saturday. In the remaining hour and 20 minutes that we have, what I'm planning on doing is I'm going to mute myself. I'll be checking the chat, and you're more than welcome to ask questions relating to navigating the course, relating to your lab reports, and I'll be more than happy to break into a private Zoom meeting where I can share my whiteboard screen and work through any problems you have questions about. This will be the end of the lecture portion in laboratory today.